So the next lecture will be given by Krishnendu Sengupta. It will be his third lecture on chaos in quantum inverted systems. So over to you.
Okay, so let us start from where I ended this morning. So we will look at the form of the correlation function. So just to refresh your memory, so we found that this correlation function, let me call it delta On, which was the matrix element of O square in this eigenstate n. I could write it as dE some e to the power beta omega by 2, and then there was a mod f square which depends on both E and omega, and then its derivative with a prefactor okay, and these f's are function of E and omega. Okay. So now, okay, one point that I mentioned is that if my f functions are reasonably smooth, which is what ETH predicts, then this second term is way smaller than the first, okay, at least at intermediate omega, that is for omega order 1 and stuff like that. Okay. However, you see that there is a beta omega by 2 factor in this integral. So therefore, for this to make sense, in the sense that for this integral to converge, so this mod f square, its first derivative, its second derivative, and everything else must have a factor which will negate this. Okay? And remember that this is multiplied by omega, this is by some other things by omega square, etc. So if you think about it, it cannot be a polynomial because there will always be a higher order polynomial in the expansion, and the only thing it can be is an exponential. And this tells you that f of E omega at large omega limit should go as exponential minus beta omega. Okay. Okay. Yeah, sorry, beta omega by 2, that is, because its square need to go as, and by the way, this should be mod omega, because, this integral, so when I do this, the gap, it can have either plus or minus sign. So my choice of En and Em can be such that this omega has a minus sign. So this, it just depends on the magnitude of the omega. But if you carefully choose all these omegas to be of positive sign, then it can be just omega, it doesn't matter. Okay. So that is one property of this f function that comes in from this correlation function. Okay. So that's the first point that I wanted to make. The second point and the subsequent thing that I wanted to do involves unequal time correlators. Okay. So this, as you know, when we worked out, this was an equal time correlation function. But now I want to do an unequal time correlator, and that unequal time correlator can be written as, so let's just write this. So I can write as something like C of t, okay, CO of t, which means that it's a correlation function of the operator O, but it's an unequal time correlator, which means that I'm writing okay. That's the connected unequal time correlator. So this again, as you can see, is summation over m not equal to n okay. So I'm going to sort of insert an identity in between, and the m equal to n term is going to just cancel this, and the rest is going to remain. Okay. So now the only difference now is that this is a function of time. And therefore what is going to give me is a e to the power I omega t. Omega being the energy difference between this. That's the only additional thing. Okay. And therefore, as before, if I write this, so let me just write one more step. So this is m equal to, not equal to n, e to the power I omega t, and minus I omega t, and then n o m mod square. Okay. Notice that, conversion of this sum into the integral is exactly same as what I did before, except that you have to carry this e to the power I omega t factor. Okay. E to the power minus I omega t factor, and that can be done. It's just another factor which depends on omega. So I can do exactly the same thing which I did before, and then what I find is that C of t, C0 of t, can be written as dE. Again, it should go from minus infinity to infinity. Sorry, it should be, okay. Whatever it was. Okay. And now I want to define a spectral function which is the Fourier transform of this with respect to omega. Okay. And this I can always do with because this form is suggestive, so I'm just going to get the this part multiplied by that. Okay. So a spectral function S0 of E omega would now become, so there is a factor of 1 by 2 pi, that's through my Fourier transform, but this would be just mod f square plus omega by 2. Okay, so I'm going to write this mod f square prime, that's the first derivative of mod f square with respect to E, and all these f's are functions of E and omega, times e to the power beta omega by 2. Okay. So the statement is that the spectral function is, and if I can ignore this f prime because it's smooth, the spectral function essentially has direct information about mod f square up to this factor of e to the power beta omega by 2. Okay. So that's one thing that one can calculate. Now, you see that this correlation function is unequal time correlator of OT and O0. Okay? But if I would have taken C0 of minus t, that is, I would have just reversed the order of O0 and OT in some sense, then I can take the linear combinations of them. The difference is what enters in things like Kubo formula or in linear response, and the sum is what enters in fluctuation stuff, and the relation between these two is essentially what gives you a fluctuation dissipation theorem in statistical mechanics. So we are going to massage this S naught, trying to define this C naught, that is this odd and even stuff, and then try to see, how to derive a fluctuation dissipation for this correlation in the eigenstate. Okay, remember that all of this is in one single eigenstate as of now. Okay. So to that end, let me first define S naught So let me first define an S naught plus and minus, which is S0 E omega plus S0 E minus omega with a plus or minus. Okay. Fine. So, so if I now take this, okay, irrespective of whether f is an odd or even function of omega, and I'm going to take this to be one or the other, this quantity remains the same if I change sign of omega, and this quantity essentially changes sign. Okay, and so does this. So S naught plus, if I define this to be S naught E omega plus S naught of E minus omega, that's going to come with a cosine of beta by 2, beta omega by 2 times mod f square. Okay, because this thing is going to, and sinh with a mod f prime square. Okay. So what you are going to find is that this is mod f square, okay, up to a factor of, let me just, yeah, 2 times mod f square cosine of beta omega by 2 plus omega by 2 mod f prime square, f square prime, sinh beta omega by 2. Okay. And the minus part would be just with this cosine and sinh interchange. Okay. So let me just write this down anyway. S0 minus would be 2 sinh plus omega by 2 mod f square cosine. Okay. So from these, I can get a form of mod f square, okay, in terms of this S naught plus and S naught minus. So if I multiply the first equation by cosine and the second equation by sinh and subtract them, then you see that this thing goes away. And so I could get, oh, by the way, everything has a factor of 2 pi somewhere, okay. So let me just write this 1 by 2 pi, 1 by 2 pi, because of this. So then mod f square should be equal to 1 by 4 pi cosine beta omega by 2 S naught plus minus sinh beta omega by 2 S naught minus. Okay. And similarly, if you wanted, you could have also found this, but this I'm not going to work on. Okay. Fine. So it's just saying that if I know my spectral functions, which comes from Fourier transform of the correlation functions, I can get a form for mod f square. Okay. And yeah. So now let's look into this S plus and S minus in a slightly more, from the point of in the time domain. So if I take S naught plus t, okay, which is of course C naught t and C naught minus t, combination of C naught t and C naught minus t, then I can write this as, or rather I can write S naught plus omega as dt of e to the power I omega t. So I have to take a Fourier transform. But this thing would be in OT O0 plus O0 OT. And minus would be just the difference. So you see one of them is the commutator, the other one is the anti-commutator. And these two, the commutator is what you get in linear response, and as I said, the anti-commutator is what you get in fluctuations. So now, therefore, because S0 minus is the commutator part, which comes from the linear response part, let me try to get the dissipation part out of that. Okay? So the imaginary part of this S0 minus is going to give you the dissipation part in a fluctuation dissipation theorem. Okay. So let me define this chi naught omega. Which is some I times and I'm going to write this in so I'm going to write this as C naught of t, the first term, and the other one is C naught of minus t, and the difference is this commutator out here. Okay. I'm just writing it with I because we'll just take proper imaginary and real parts later. Okay, so this is chi naught of omega. Now I can substitute this C naught t, etc., everything here, because I already know what this C naught t is, okay, in terms of f's and stuff like that. So the first term is going to have e to the power I nu t, and the second term is going to have a e to the power minus I nu t, and then I can write this down with two terms. One of them proportional to e to the power I omega plus nu, and the other proportional to e to the power I omega minus nu. Okay? So just substitute this C naught t by integrals over dE and stuff like that, and then that will. So from here, you have to do what you need to do, and I'm not going to do this in details because I don't have time, but the point is that if you take the imaginary part of this, that integral can be done because all you are going to get is a delta function, because this e to the power I omega t, its integral. Over time will just give you some delta function. And once you do this, you will find that this, using this, the imaginary part of this chi naught, and this algebra is carried out in details in the review article that I referred to. So, in case you are interested, you can just look at that. Is 2 pi sinh beta omega by 2 times mod f square. This is almost equal to, because I have neglected the del f prime, this derivative term, talking into smoothness. Okay? But if I do neglect that from here, okay, you see that, so I had an expression for S naught plus somewhere, this one. Then in that limit, this would be just 4 pi times cosine beta by 2 times mod f square, if I neglect this. So S plus is almost equal to 4 pi times cosine beta omega 2 by mod f square. Okay? And now you see that if I write one in terms of the other, because both of them has mod f square, then I get the relation that imaginary part of chi naught is 2 cot h beta omega by 2 times S naught plus. Okay? And because this is my linear response, this is the dissipation part and this is the fluctuation part, this essentially gives you a fluctuation dissipation theorem. And the interesting thing about this is that this is not after summing over all the eigenstates of a system. just taking a single eigenstate out here. Okay. And therefore, every eigenstate has a corresponding fluctuation dissipation theorem with a characteristic energy beta, which is the average temperature or energy of the system. And this statement is what it, at least, one way of interpreting the statement that the thermalization occurs eigenstate by eigenstate. Okay. Corresponding to everything, you have this kind of. And of course, it will, because beta is a function of E, the average energy, it depends. If your initial average energy is something, the temperature would be temperature corresponding to this fluctuation dissipation would be something else and stuff. Okay. So, is that okay? Or
can you please repeat what you said that it happens ideally?
Oh, what I mean is that, look, I got a relation between linear response, that is the dissipation part and the fluctuation part. But if you think about it, I was just computing matrix element in one eigenstate, that state n. Okay, so corresponding to every eigenstate there is this thing. So there is a fluctuation dissipation for individual this thing, characterized by a temperature. So thermalization or assigning a temperature happens eigenstate by eigenstate. That's the statement. Okay.
So this linear response, and there is an underlying response structure that
Yeah.
the system is in equilibrium, I turn on a small field and the change.
No, but here you can be far away from equilibrium because your initial state could be anywhere. So you don't need to be in fact, if you are in ground state, then this is not going to work.
No, so what I'm asking is that does it have the structure of linear response, or is there an underlying linear response happening somewhere? Because
No, the structure of these correlation functions are of linear response.
where did we use linear response?
Why did we use linear response? So essentially we use linear response when we showed that this C naught T can be written as, or rather this S naught minus out here, somewhere out here, no? Yeah, S naught minus could be written in terms of expectation of OT O0. I mean, it's not linear response in the sense that you are retaining just the first order term or anything like that. But all I am saying is that here the commutator is very reminiscent of the Kubo formula, and that's the thing that I'm, so it's some response function, okay? I'm sorry? No, I think it will be cottage probably, no? Yeah, maybe one way or the other, just figure. Really? Okay. Okay, switch sides, no problem.
No, so Krishnendu, so what I'm asking is the following. I mean, Kubo, the way he derives it, his relation is the following, that the system is in equilibrium and I apply a small field and I ask how much does the field induce, how much change does the field induce, and I see that the response is related to the equilibrium correlation in the absence of the response. Can one do a similar calculation within this ETH format that I
No, here, no, so here I start with an initial state. The point is that then I ask that, given that initial state, let's say some state, I want to find out, no, actually, no, I'm sorry. What I'm saying is that here, what I'm doing is that I simply start at a given eigenstate, okay, and I want to see what is the structure of this correlation function in that given eigenstate. So in doing this, I don't really have a external probe or anything like that. So it's not Kubo in that sense, So maybe I should not use the word linear response, but the point is that the correlation function that ultimately comes in as the susceptibility or whatever response function Kubo gives is remarkably similar in structure to this, okay? But here there is no field or no, not anything like that.
Can one interpret this as the following, that say I have some Hamiltonian and I add some perturbation to this.
Right.
So this is one way of looking at how eigenstates are sensitive to that perturbation.
Yeah, you could say that probably because you are calculating correlations in that. Yeah.
So,
Yeah.
so in that sense, it would be what Shamik is trying to say, like that this is the linear response at the level of.
Which is the perturbation?
No, but there is no perturbation per se. You see, you have a eigenstate, and then you just want to calculate the correlation there. So it's not like I am tuning my system with an external perturbation and then seeing the response. It's not response in that form. So you can say that, well, you know, I can think of this as poking that eigenstate with an operator O and try to see what the state does after a time t. But I mean, this operator O is not a field or anything, external field or anything like that. I mean, so yeah. Okay. In any case, so, okay, so now the last thing that I want to do in case of, for this ETH kind of thing is to look into the behavior of this mod f at different these things. So I just wanted to list them, you know, just for completeness. So f becomes a constant when the frequency is low. And that is understandable because, you know, if the frequency is really low, what it means is that you are in a small energy window because that's the maximum frequency you are allowed, right? Which essentially means that you must go to the random matrix theory, which essentially means that this f has to be a constant, okay? And it turns out that this constant goes as square root of 1 over L, the system size, okay? And in a minute, I'm going to give you a derivation of this, why this happens, but let's just. Remarkably, so this is one point. Remarkably, this root L behavior, when you do these things numerically, it extends to a pretty large range of frequency. So if you scale your frequencies up by your you know, typical energy scales in your Hamiltonian, then it goes all the way till intermediate frequencies, you know. This is a numerical fact. People do not understand why, and not at least analytically. And then when you go to really large omega, that is you are extending your domain, for large omega, f decays as exponential minus omega, sorry, mod omega. Why omega square? I'm getting confused, right? Yeah. With this beta, okay? That we showed. So these are the behaviors, and overall f has to be a smooth function. And these are the behaviors that typically characterizes an ETH f for a ETH obeying system. Okay. So let me show you just a few slides where they have essentially shown this, you know, this done some numerics on a finite chain and looked into this ETH thing. So can I? I think this needs to be connected somewhere. No, can you see which one? Or maybe this one. Yes. Yeah, okay, thanks. Why is it not? Oh, it's not moving. Or maybe I should, oh, okay, it's moving but very slowly. Let me see. Okay. Okay, good. So the first thing that I wanted to show is a numerical demonstration of ETH obeying and ETH non-obeying systems. So again, they were taking this Hamiltonian, where you have a nearest and the next nearest over term, and an interaction term which is not written here, but that's given by V and V prime. So nearest neighbor and next nearest neighbor, density interaction, and it's a bunch of fermions on a lattice. So you see that when my J prime and V prime is 0, when I just have a free fermions, you see the spread of this thing. We calculate. So what one calculates is this MK, this expectation. So these are hardcore bosons, not fermions, sorry, but hardcore. It's almost same as fermions. Hardcore bosons as a function of energy per site. So this is what they calculate. Okay. Now the point is that this spread, and you see the behavior of here and there, it's very different. Okay. Here the spread is way more, and here it's almost living on a band. And it's living on, so the point is that, these are finite size systems, so there is still a spread. But this is even better, this thing, if you look into this KPP, which is defined as this, some operators like this, which contains both nearest and the next nearest neighbor term. And that, for this kind of 0.16, just follow this energy dependent. This EP is the initial energy of the state. Okay? So it just depends on this energy of the state. Here the spread is even more. Okay, see, there's a lot of spread. So this is sort of a demonstration that for integrable models, it's not just a ETH obeying energy dependent function. It's spread way over than the energy line, and here it is just a function of energy. And here is what I wanted to show about this, the spectral, this F function. So this is what this F function looks like. So at large omega, where you have this, you see that this it's in a logarithmic scale, so it goes down as e to the power minus beta omega. Here, this is at a very small omega scale. And the reason why it is small is that, look, there is a factor of L square sitting here, okay, in the x-axis. So these numbers may look the same, but it's actually, omega is very, very small here. L square is, of course, order 100 or so. Okay. So the point is that here you see from the y-axis scale that this has almost become a constant. Okay. And intermediate behavior is messy, but as they say that at intermediate omega, it's still proportional to square root of L. Which is what is numerically seen. This is guaranteed by equivalence with RMT. This is guaranteed by the fact that, this is guaranteed by equivalence with RMT that F will become a constant. This is needed for convergence of all correlation function. So these two are very basic. Here, of course, it's a numerical fact, and I don't really know if there is a deep reason for this being square root of L. Okay. So typically, if you have a dissipative system, where this correlation function goes as 1 over square root of t in d equal to 1, then you can show that this would be square root of L. But this region is not necessarily the dissipative region in a Medibody system. Okay. In this intermediate omega, it can also be the ballistic region. So I don't know if that explains it or not. Okay. So I think this is all that I wanted to say about eigenstate thermalization hypothesis. Okay. So the ETH part of it, how it applies to quantum systems. So the basic point is that, usually if you don't impose any structure on correlation function, what happens is that your answer from quantum mechanics and the answer from StatMech, there is no way to reconcile them. Now, random matrix theory gives you a way of reconciling them, but it doesn't give you the necessary energy dependence that the StatMech predicts. And ETH is sort of a way of putting into that energy dependence, that hypothesis, into the structure of the into the matrix element of these operators, local operators. So one thing that is there is that numerically it is seen that it's only these local operators that obey this ETH kind of structure. Although this thing is not very well understood in my opinion. And also this is just a hypothesis, it's not proved yet, but it gives us a way of understanding most of our numerical results on when we do quench dynamics or that kind of thing in a quantum system. Okay, so if you have any questions on ETH or anything related to that, I can take it now, and then next I'm going to move to the other section. Yeah. The Y ergodic. Yeah, so the point is that if a system, if a Hamiltonian system is such that there, apart from global symmetries, there is no conserved charges, okay, then your steady state is determined just by its energy, and that steady state therefore is thermal, in the sense that, if you start from an initial state, the steady state is going to depend on the energy of that initial state. If you are talking about microcanonical ensemble, and if you are talking about canonical ensemble, it's going to depend on temperature. However, and usual stat mix tells us that this kind of system essentially leads to exploration of phase space. Okay, that's the standard sense of ergodicity. That, however, think of a classical system. If you have a lot of conserved charges, then those put constraint on the dynamics in phase space, right? You can hang around in a circle. Think of an oscillator, okay? You're going to just go around a circle in phase space. So in those kind of systems, you cannot explore the full phase space, okay? And in that sense, it's non-ergodic, and there is a distinction between these two, okay? Make sense? Okay, if not, let me move on to, this other part. And now I would like to take this off actually. So this. Okay, so so we saw that eigenstate thermalization hypothesis usually works for this ergodic systems, and however, in the kind of quantum systems that you come in, there are ways in which this ergodicity can be violated. Okay, and so let me list a number of ways in which they can be violated. One of them is integrability. Okay. This is something we discussed, at least in the context of random matrix theory. So if there is a large number of conserved charges, that essentially breaks this ergodicity, and ETH doesn't hold for that kind of stuff. And we already showed that, we already saw that at least in the context of random matrix theory, the structure of energy eigenvalues, etc., are all very different in this case. So there is no surprise that if you have these conserved charges, that ETH is not going to work. Okay, this is not for ergodic. The second way, again, by breaking ergodicity, because of breaking of ergodicity, is when you add a very strong disorder. Okay, so previously we of course knew, when in the 90s when we were growing up, we knew about this Anderson localization disorder, and in non-interacting or weakly interacting system, this will completely localize. But then a more defined version of this came up, and this is this many-body localization, where eigenstates in Fock space get completely localized. due to strong disorder. And this is also another statement which says that, if such a phase occurs, then the system is no longer ergodic. You put something in one eigenstate, it simply doesn't move. Okay. But these two are not the things that I want to talk about. Okay. This is going to take at least one more lecture which I don't have, and this one we have already talked about a little bit. But more interestingly, there are two other phenomena that I want to talk about. One of them is called quantum scars, that is a special class of eigenstate whose presence essentially violates this ETH. So, scars. And fourth is sometimes in a constrained Hamiltonian, because of the presence of constraint, or maybe because of something else, the Hamiltonian essentially gets fragmented into dynamically disconnected sectors. And there are exponentially large number of such sectors in your computational basis. So for example, if you are writing this Hamiltonian as a matrix in your Fogg basis in real space, then what happens is that you are going to see dynamically disconnected islands and an exponentially large number of them. That phenomenon is known as Hilbert space fragmentation. The name is pretty obvious. And I'm going to call this as HSF, okay, just for not writing this over and over again. So essentially, these two are things that I would like to discuss in today's and tomorrow's lectures. Okay? Two modes of how this thing can happen. So in today's lecture, I'm going to start with this presence of scars. Now, scars have a long history. It started in classical systems, where the people have seen that there are. So in classical systems, what happens is that if you take one such system, such a billiard ball, and you let it move, most of the trajectories essentially is going to cover the entire phase space, if you start from one bit. But there are special trajectories which doesn't, and those are the scar trajectories. So that is in the context of classical this thing. In context of single particle quantum mechanics, I think it was Heller in 1984 who wrote a very beautiful paper where he took one of these billiard ball, this thing, something called a Buvinovich stadium. So it's a really interesting get-up. It's just, things like that. So, and the classical system, a ball just wants to move out here. Okay, so that's and certain trajectories essentially doesn't cover the entire phase space. But what Heller did was very interesting. He took this as a potential in a otherwise free quantum mechanical problem, and then studied the evolution of a Gaussian wave packet. And he saw that when the center of that Gaussian wave packet is centered around one of this ergodicity violating trajectory, that doesn't fill up the entire, so the probability distribution doesn't fill up the entire space again. Okay. So those were called as, in the trajectory sense, they were called as quantum scars. But the scars that I am going to talk about here, and what people talk about in the context of many-body physics, are special class of eigenstates which are protected from otherwise thermal eigenstates in the middle of the spectrum by some emergent symmetry or for some other reason. So I'm going to only talk about cases where there is an emergent symmetry which protects these states, and I'm going to give example by a model. Now, imagine that your Hilbert space has a lot of states, and in the middle of the spectrum, everything is thermal. Okay? So usually, if you wanted to see some kind of correlation function, it's going to show thermalization, because if you pick up a state, it will be thermal, and then as we saw, that it will give a thermal result. However, if there is a bunch of state which is protected by some symmetry, they do not interact with this thermal state, then it can give very different results. And that's why, and if you see dynamics or expectation value of anything, starting from one of those states which is there in this symmetry preserving sector, you will see a very different kind of behavior than what ETH tells you. Okay? So that's how this thing is violated. So to make this point more clear, let me give a concrete example where this kind of scars occur. Okay? And fortunately, there is one very simple model where all of this can be analytically worked out. So I'm just going to do that, and then I'm going to probably later tomorrow, either later part of today's lecture or tomorrow, I'm going to start to show you some plots about some realistic systems where this kind of scars come in. Okay. Okay, very nice. So the model that I was thinking about is this Hamiltonian. Okay, simple xy spin chain and then a magnetic field. Okay, but these are spin 1 objects. These are not spin half. Okay, so that's the first thing that one needs to do. So in on-site, there are 3 states per site, and these are given by eigenstate of Sz, and I'm going to call them as plus, 0, and minus. That's the plus 1, 0, and minus 1 eigenstate of Sz. Okay. Now, if I am if this magnetic field is really strong, and let's say it has, let's say it's negative, for example, for this sign, then the all down state, that is all minus state, is your ground state. Okay, because remember that S plus S minus acting on that is simply going to annihilate the state, because there is one S minus which is going to annihilate the minus, so that's okay. And then this BSZ essentially gives you the energy of that state. Okay. So I'm going to start from a ground state, omega, which is minus, 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 and so on. That's my fog state. I could have as well started from the all plus state. It doesn't really matter. Okay. Okay? Now, once this is the ground state, the first thing you can think of is that what is the, the low-lying excitation over this ground state, and that's the first thing that one does. And these low-lying excitations are essentially what are called magnons. The particles which would move. So, how do you see that? So, for example, now if I create a state, let's say by Sj plus acting on this ground, okay, that's going to give me a state minus, minus, etc., and then 1, 0, and then all minus again. Okay. Remember, S minus acting on, so S plus acting on this minus gives you a 0, okay, and so on. So the algebra is that S plus acting on minus is 0, and S plus acting on 0 is square root of 2 times 1, and so on. This is a typical spin 1 algebra. And the matrices are, of course, spin 1 SU2 matrices, which we all know. So I am not writing them down explicitly. But once you have this 0, think of the Hamiltonian acting on this state. Okay? So this Hamiltonian can act on this state so as to convert this into a minus and the rest to a 0 again. So in other words, this 0 can move through the lattice by the action of the Hamiltonian. Okay? So therefore, if this is a state I call J, okay, then the action of the Hamiltonian on this J, this H acting on J, can give me a state which is J plus 1, or can give me a state which is J minus 1. It's of course going to, it can not give me any other state, because acting anywhere else is going to just annihilate the, okay. Is that part clear?
Can you repeat it? Sj plus Sj minus, that would be Sjj or Jj plus 1?
Jj plus 1. Sorry. Okay. Just think of that as J plus 1. Okay, let me write the Hamiltonian here again, that term. Plus Hermitian conjugate. Sorry about that. Okay. So Hj, so
Another question, if that is the case, then how all down is the ground state?
oh, because there will always be a Sj minus, right, which is going to annihilate the state.
Oh, okay.
That's the point. Okay. So the situation here is a bit different for spin 1 compared to what we are normally accustomed with spin half. So yeah. Okay, so if I act this Sj plus on this vacuum, you are going to get a 0. That you see, right? Then suppose I do this at the jth site. Okay. Then this is a state called j. It's just the location of this 0 that gives me the state. Okay. Then if I act on this h with on this j, I can have a state where this Sj minus acts on 0, and that will give me a minus, and the corresponding Sj plus will act on j minus 1 or j plus 1, whatever the term is, and that will give me a 0. So effectively this 0 has either hopped in this direction or hopped in that direction. Okay? So that's how this thing. But this we already know what this is. This is just like a single particle hopping on a lattice. Okay? Because the state j goes to j plus 1, that's like hopping of a single particle. And of course the magnetic field out here essentially is going to give you some chemical potential for that particle. Because this 0 has a different energy compared to minus, and therefore creating that 0 has an on-site cost. Okay? And so if you work on this, you can diagonalize this hopping problem, and you can get a band of energy in momentum space, and that is given by some 2j cos k, that's from these terms, minus whatever that term is, mu. Okay. That will depend on the magnetic field. So it's basically a single particle band, and these are your Magnon states. Okay. So this is standard excitation spectrum of this model. Is that part clear? Any questions? I'm sorry? Oh, mu. This is just, okay, let me just do this explicitly. So if I have a minus, I will have a minus p and then 0. Just b. See, this magnetic field term has a different energy of 0 compared to this thing. That's the on-site energy of creating that excitation. And this actually is a plus b, I think. So the point is that this energy cost is compensated by this hopping, that it gives you a band. So this is the typical magnonic band in a spin system. Okay. Now suppose, okay, fine. So this is nothing unusual, these magnons happen in many spin systems and all that. But now the thing to realize is that there is another class of state, typically called a bimagnon, which can occur in these systems, and they have a very special character. So let me try to get those. So before writing down formal operators which creates these bimagnons, let's just try to see one small thing. Okay. So I have created this state, this excited state, by creating a operating with Sj plus 1s on this ground, right? But I could do this twice, because, and after that of course it will annihilate, okay? But if I consider Sj plus square, okay? Yeah. Well, if you are writing things in Ek, then it's a periodic chain, but forget about boundary condition. I'm just talking about the bulk right now, okay?
But Sj plus square is not lower in just above the...
No, it will be a, see this excitation, what it's going to do acting on ground is going to give you minus, 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 then a plus, and then minus, 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 okay? That's the thing.
Like second excitation kind of.
It's a, yeah, so if you are just in the local limit, then this will give you a twice B energy gap. Yeah, okay. So now think of a given plus minus pair out here. Okay. This term Sj plus Sj minus converts this pair into 0, 0. Because Sj minus can act here, Sj plus can act there, and is going to give you a 0, 0. Okay. Now, but I could have created this plus either on an even site or an odd site. It doesn't matter. I can create it anywhere, but I can have a thing where this is 2j and this is 2j plus 1. Okay? But I could have done this the other way also. I could have created a plus sign at, let's say, 2j plus 1, and then the minus would be at 2j minus 1. Either way, the action of h plus on this is going to give me a 0, 0. All with all sudden. Therefore, if I define an operator j plus, which is e to the power I pi j times sj plus square, okay, which is going to create a superposition of this plus minus and the minus plus pair for me with a minus sign. The Hamiltonian acting on that site is going to give me 0. Okay. Is that part clear to everybody, or?
Can you repeat that once?
Yeah. So, see, I have created a plus on a side j, right? Now, I can do this on an even site or an odd site. That's up to me, right? If I had an even site creating this plus, then this is my configuration, and this is going to, so we saw that Hamiltonian acting on this, the kinetic part of the Hamiltonian, the xy part, acting on this is going to give me a 0, 0. But think of doing this the other way around. So it had a minus and a plus out here. So suppose I would have created my excitation on the j plus 1th site, 2j plus 1th site, then this is also going to give me a 0, 0. Nothing else can happen, right? I can lower 1 by plus to 0 and raise minus to 0. That's all. Therefore, if I consider an operator like this, which creates excitation with a sign, depending on whether it's on an even sublattice or an odd sublattice, then it's going to give me a superposition state of this and the minus plus counterpart, right? And then Hamiltonian acting on this must give me 0. Okay. Is that part clear, or do I need to explain more?
Now, because you have a sign, so what is the algebra this operator satisfies?
No, I'm coming to that. But this is not the full story. I have to, yeah.
I understood why you introduced J plus, but how does Hamiltonian become 0? Action of Hamiltonian
Well,
become 0?
this plus, the Hamiltonian acting on this plus minus is just going to give me a 0, 0. But if this was minus plus, it would also give me a 0, 0. So if you create a super, yeah, right, okay. Okay, fine. So then this tells me that I can construct operators, which is summation over j, because there is nothing special about j, states like this. Okay, and then I can consider a series of states, which is, I'll call them Bn, which is this j plus acting on this n times on vacuum. Okay. So every time it acts, it's going to give me this up down minus down up pair. Okay. And because I cannot create a up down minus down up pair simultaneously on the same site, it's just going to give me linear superposition of 1 pair, 2 pairs, 3 pairs, and so on. But what's the energy, on-site energy of this state? So if I have a plus, then clearly, this is 2 times B, because from the ground state. Okay, and so if I have n pairs, I'm going to have B 2n minus L. That is, minus BL is of course the energy of the ground state, so I'm just subtracting that. So this is delta epsilon. Yeah. Okay. So all these n states now form a tower, linearly dispersing tower of states, which are out there. Okay. And this is not touched by any other state because these are exact eigenstate of the Hamiltonian. So it seems that there is a linear tower of states called the bimagnant states, which do not disperse, by the way. These are constant, they do not depend on k. And these states form a tower. Okay. So these are typically the bimagnant states. Third part, yeah.
So why you apply the Z plus for n times? So it's J plus only create plus minus plus minus plus minus.
So no, J plus can create, so one action of this J plus is going to create, many states. So, but it will be only one pair in each of these. At different J sites, all right?
Yeah, that's why sum.
No, the sum is over spatial J's. So it's going to create one pair. So it is going to give me all states with one up-down pair at different sites. But then, of course, I can also think of having two up-down pairs. Then I have to apply J plus again and so on and so forth. So therefore, in general, you can have n such pairs. And of course, n is constrained only by the system size. Okay. So n can be at most L by 2. Very good. So the interesting thing about this bimagnant tower of states is that it has an additional symmetry. Okay. So it turns out that if you have this J plus, which is this operator, okay, and this Hermitian conjugate J minus, which of course takes a pair and annihilate that, and Jz, which is half of summation over J is Jz, the total spin, they form a SU2 representation. They satisfy this SU2 algebra. Okay. This one can check, and the simplest way to check this so the simplest way to check this is that you take a given state with n pairs, act on J plus and J minus on that, okay, and you are going to see that so basically, if you take this commutator J plus J minus and you act this on a state, let's say some state B, n, okay, you see that it's going to simply count the number of times it can annihilate a pair. Okay, and here how many pairs it can create, and this would be proportional to J of Z, because that's the total spin of the system. Okay, and you can do this much more carefully. Just do the algebra, and this, it turns out that this J plus minus and Jz forms a spin L by 2 representation of SU2. Okay. So, interestingly, what that means is that J plus acting on any state omega Bn, okay, is going to take it to and there are factors of n here. I don't remember the factors offhand, but it's a L by 2 representation. Sorry, S into S plus 1. L. Okay. This is a typical angular momentum algebra, but with a spin which is L by 2. And similarly for J minus, it's going to take it to 1 minus 1. Now, you see the interesting thing that these states, so this SU2 symmetry only belong to the sector of states which are these bimagnons. It was not there in the original Hamiltonian. If you look into the Hamiltonian, there is no SU2 symmetry there, it just follows a U1. The Magnon states that I had can be understood as a consequence of that U1 symmetry, okay? But not this. This is an example of what in condensed matter in context of scarce is called an emergent symmetry. It's not there in the full Hamiltonian, but a subclass of state can be described by an effective Hamiltonian which has this symmetry. In this case, it's really this apparatus which is going to give you the representation of that symmetry. So this leads to an emergent SU2 symmetry. Okay?
Can you please why these bns are the eigenstates and how to understand that?
Oh, because if you take a Bn, it has a superposition structure such that H plus annihilates this. You see, I did this for a single this thing. So if you had a plus minus pair, then it goes to 0, 0, and a minus plus pair also goes to 0, 0, and I'm doing this with a relative minus sign. So n pairs are also going to do the same.
J plus, J minus, JC are an angular momentum operator.
That's right.
It's different from that J plus.
Yeah, it's different because this is a spin L by 2 angular momentum operators, but the other ones were a spin 1 angular momentum operators. Okay.
So corresponding to this emergent SU2 algebra, you will get some emergent conserved charges which...
No, what I'm going to get is going to be clear when we discuss dynamics here. So if I look at the correlation function of dynamics like this, so the point is because these states has some protection, because of this emergent symmetry, if you start from a state which belongs to this sector, its dynamics is never going to go to the thermal states outside this sector. Okay, so this symmetry, so you can think of it in terms of having some conserved charges, essentially protects that sector of the states. Okay. Is that part clear or? Fine. Another interesting part about this, which is also pretty general when it comes to quantum scarce, is that you see that within this subspace of states, H J plus is just some omega times J plus. Because this you can see by applying this J plus on any other given states. Because you see that if I have a state Bn, J plus acting on this Bn just gives me n plus 1, Bn plus 1, and the Hamiltonian will give me some energy. The other way around, it's going to give me an energy of one less pair, right? So Hj plus on Bn is H on Bn plus 1, which is equal to En plus 1. And J plus of H on Bn is En times Bn plus 1. Okay? So the difference is essentially the difference between the neighboring eigenstates in this tower. Okay? So, and I call this difference to be omega. Okay? This is the operator form of this thing. Okay? So the point is that this is what is called a spectrum generating algebra. Okay? That raising operator, this is really harmonic oscillator. Okay? A raising operator essentially takes you to another state and then this is going to give you something. But this happens in a complicated context where everything is emergent. So the spectrum generating algebra is also emergent because this doesn't work for other states. It's only this subclass of bimagnon states that essentially creates this spectrum generating algebra.
Sir, can you tell why you call this tower states?
Because there is a tower of energy eigenstates. Because the first, it's like, it's the same sense you call harmonic oscillator states as a tower of states. Their energy difference is exactly a constant. That's it.
Spectrum is bounded from above, right?
Yes, that difference is there with harmonic oscillator, but yeah. But tower in the sense that, tower can be a finite tower. Yeah, it's a, same energy difference, that's all. Yeah. Okay. So now, let us just see that, so now the rest of it is actually a bit numerical, but let me just tell you about two, this thing. One of them is that if you are starting from an initial state within the tower, and if you are evolving this with your Hamiltonian, so let me just do that, and then I'm going to show you some plots and then end this part. Oh, okay. So imagine that I have an psi of 0, which is like one of these BNs, okay? And I wanted to basically, or maybe I can just take some Bn with Cn, okay? Then psi of t, which is e to the power minus iht by h bar acting on psi of 0, is simply going to act on these Bn's, but because it's a tower of states, okay, I'm just going to get some Cn e to the power I okay. Therefore, the fidelity is going to oscillate, okay, because there are lots of them, and there will be some, and there would be a particular frequency after which, when this all of this n epsilon minus, so the gaps, the frequencies of oscillation would typically be epsilon n minus 1, and so on and so forth. If you take one phase factor out, that's what it's going to be. Now the point is that you see that this oscillation is going to repeat, because there will be some time after which the largest of this will be just 2 pi in that time. So this will be an oscillatory function. So, but however, think of what ETH would predict. ETH would predict that if you start from such a state, you evolve this, it's going to rapidly scramble and be there in all of the Hilbert spaces, right? So its overlap with the initial state has to go to 0, or at least 1 by the Hilbert space dimension, okay? So ETH is going to say that this f of t, which is psi t psi 0, is going to rapidly go to 0, okay? Whereas this is going to give an oscillatory behavior. So this is one of the examples where there is a clear violation of ETH in this kind of systems, okay? And I'm going to show you some plots in a minute, but let me just try to do one more thing and then we can, yeah.
So here, like where this is like periodic revival, what is happening? This is due to the fact that the energies are kind of multiples of each other, right? Or like
the gap is constant, yes, sure.
But is it necessary that all the cases I will have a tower of state? So then I will not have this period.
You are still going to see oscillations, but they are not going to get back to 1.
Okay, so that will kind of
yeah. So I'm also going to, maybe tomorrow, I'm not entirely sure, but maybe tomorrow I'm going to show you some examples of that. Okay.
So here the point is that the Hilbert space is not it is not fragmented. Like
no. No, it is in the sense that, this states which are in the sector with this emergent symmetry, they effectively don't talk to the other thermal state. So you can think of this as having two fragments, one large fragments with the thermal state, and here order L number of states which do not have this. So
one doesn't call it HSF because
one calls it a weak HSF, and I'm going to make that classification clear when I discuss Hilbert space fragmentation. That's a very good point actually. But yeah, so the point is that the other thing that one can calculate is an equal time correlator between, in any of these states, Bn, I can calculate a J plus J minus acting on this, okay. Let me call it some Cn. Okay. Now you see that this is just going to give me this. So this acting on this is going to give me a Bn minus 1, and then this J plus acting on is going to give me Bn. So what is going to come out are these factors, of square root of whatever. So whatever is there, but the leading behavior is always L square. Okay? So if I define this correlator with a factor of 1 over L square, then, and there is another one, of course. So all these factors that come in the angular momentum algebra, but because it's a spin L by 2 algebra, there will always be this factor which is the leading thing. Okay? And therefore, this thing is going to go to 1. So 1 by L square. And in fact, there is an exact expression for this. It turns out that the answer is 2n minus L by L whole square. Plus 1 and etc. Okay? So this is the second leading power and all that. But however, the leading thing is ordered. ETH, on the other hand, if you calculate this Cn using trace rho dE times this operator, J plus J minus, if this was a ETH obeying system, or you take a initial state which is thermal, this is going to tell that this thing is going to go down as L to the power some alpha. Most likely it's linear, I don't remember exactly, but the point is that it's going to decay with system size. And this is going to go to a constant value with system size when you see. So that also is one difference, okay? That ETH prediction out here is different from ETH prediction. And look why this is getting different, because the point is that these J plus and J minus, which are reasonably local operators because it's sum of many local terms, is almost well, not quite an eigenstate, but it's not changing this Bn substantially. In fact, the operator of J plus J minus combination is bringing this Bn back to it. This almost never happens in an ergodic system, that if you have a local operator, it takes this eigenstate, which is a very complicated combination of Fock state, and spreads it all around. Here, this is not happening, and the reason why this is not happening is the emergent symmetry. Okay? So in this sense, this emergent symmetry leads to violation of ETH in this thing. Okay? And also one can calculate the entanglement entropy, which is again completely numerical exercise, but you can do. So what you do is that you take a state, constitute the density matrix, and then trace out the states in that density matrix which has weight on one half of the chain, and compute what is called the half chain entanglement. Now, this half chain entanglement gives you, I think, a log behavior for this kind of states, whereas ETH will predict thermal behavior, which is like L. Okay? So essentially, all of these characteristics that you can measure out here tells you that if you are starting from one of these states with an emergent symmetry, you are not going to see ETH prediction. Okay? So in the next lecture, what I'm going to do is to take up another Hamiltonian system called the Rydberg chain, where this kind of quantum scars come in, but these are not as kosher as the quantum scars here. They are not exact quantum scars. They have some, they are approximate quantum scars, and I'm going to make sure what I mean. I'm going to explain what I mean by that. Okay.
So these J operators, they don't satisfy ETH, but other operators in this?
No, any operator, when you start from this initial state, if it's a sufficiently local operator, the statement is that it's not going to give you a result consistent with ETH. Okay. You can check with other operators. Usually, the best thing to do is to check for fidelity and entanglement, which are not this thing. And if that is different, usually correlations will also be different. Yeah?
Suppose I write down an Hamiltonian. So is there any way to know that this Hamiltonian is going to have this emergency?
This Hamiltonian is what? Can you speak up?
Like this Hamiltonian is going to have this kind of emergency.
Oh, no, that is, no, the reverse problem is difficult. So people have essentially known many other Hamiltonians. So for example, one of them is the Hubbard model, where there is something called eta pairing where this kind of scars take place. The AKLT chain is another example where this kind of scars happen. But if you tell me that, I want to write a generic Hamiltonian which will have this, I don't know the answer to that. Okay. But Sanjay and others, they have a very nice review article where they have thought about a systematic way of constructing these many-bodied scars in eigenstates of and embed them in an eigenstate of a given Hamiltonian. Okay, so that kind of techniques people use sometimes, but these, to the best of my knowledge, are pretty complicated in the sense that they require complicated numerics and analytics. I mean, it's not very straightforward, this thing. But I'm going to sort of, in the next class, I'm going to sort of give you a list of references which covers this. Okay, so and yeah. Yeah.
So, what are the necessary ingredients to be present in the Hamiltonian equate scars?
No, that question I don't know. You see, the point is that that's exactly the same question that he asked, and the answer is I don't really know. So there is no. So to the best of my knowledge, if I give you a Hamiltonian, you have to run some numerical diagnostics before, or be very clever and see a symmetry, emergent symmetry pattern. Okay, things like that. But generically, I don't really know.
But is it guaranteed that if there is emergent symmetry, that will be scarred?
Yes. If there is an emergent symmetry, an exact emergent symmetry like this, then of course states in there. See, one of the way of thinking about this is that one of the reasons why ETH works is that there is an exponentially large number of states which is surrounding your initial state. Here, if you are within the tower, it's just order L states. Now immediately you will see that the dynamics is very different. Okay? The dephasing which leads to this thermalization because of the presence of a large number of states is not going to be here.
It is like restricted within some.
Yeah, it is restricted within a subspace, and that restriction happens because of this emergent symmetry. So once it is here, then you are done.
Here you constructed these states as a low-lying states in the original Hamiltonian. So they are already far away from the third.
No, because you see the point is that energy was proportional to n, the number of pairs. So it's going to go all the way from below to the top. Okay.
But typically I won't be able to see this in a, suppose I run the dynamics because these states are atypical.
Yes. So you need to know which state to start from. So the reason why these cars gathered a lot of momentum in the PXP chain was that one of the state was a nil state which they can actually manufacture in experiments, So it was a pure stroke of luck. AKLT model, for example, they have a beautiful this tower of states, but the states are so complicated superposition that nobody is ever going to be able to construct them in a laboratory. And those kind of dynamics will be very hard to see. So you need that, thing. Okay, can I just show a few these things and then we'll call it a day.
Sir?
Yeah.
So for example, if we have some Hamiltonian, and how can we tell if maybe we see that it follows ETH, but that there are not some special states which...
No, actually it's a very difficult question because the point is that, if these cars, so here these cars are reasonably simple states, simple in the sense that they have very, so they can be analytically constructed or, they are close to some Fock states which is easy to understand classically. But if that's not the case, then those cars might be there, but you might not be able to detect it. One thing that you can do though, you can take all eigenstates and construct and compute their half-chain entanglement and plot that as a function of the eigenenergies. Usually, if these are standard cars, they are going to have a lower entanglement, and then they stand out from the thermal bunch. Yeah. Yeah, so here is a picture. So this was the wave function overlap, okay? So the blue one, okay, so the blue one is something which is in the scarce sector. Forget about this pneumatic nil, etc., this thing. And the red and the green ones are in sectors which are outside this this thing, okay? So you see that one of them goes with this oscillation and the other goes this rapid thermalization. Okay? The other thing that I wanted to show is that if you look into this plot out here, this is a plot of half chain entanglement. So you take your chain and split it into two subsystems A and B and trace out states which have weight in B and then divide this SA by log 2. Okay? So the point is that this is your thermal band, and you see in the mid-spectrum region where ETH is supposed to hold, this is really like a volume law. This has large entanglement. However, there is this band of states, which is incredibly low entanglement. This thing. You see these red dots? So these go as log L, just as I mentioned. Okay, and you see that even in the middle of the spectrum, where everything else is thermal, this stands out, okay, from this thermal band. And remember that the fact that this band has a spread is a finite system size effect. So if you could have gone to really, really large system, this spread is going to decrease, and then everything would be something like thermal states out here, except these, okay? So this tells you that these states do not obey the normal ETH-like behavior, okay? So that's the thing about this spin 1 scars. And okay, tomorrow I'm going to talk about this scars in the PXP model and stuff like that. So I think we should call it a day. It's almost 4. So okay, so I think one way in which we saw violation of ETH in this kind of system is by the special eigenstates, which has an emergent symmetry. In the next lecture, we are first going to see these, another example of these, and then go to the second phenomenon, which is Hilbert space fragmentation. Okay, so that's the plan. Okay.